Good day, everyone. I welcome you back to Global Education Zone, the home of impactful learning. It's nice over here for you and I because learning never ends and education is the key to an impactful life. Everyone, my name is Anthony Nathaniel and I welcome you back to Global Education Zone. In this particular episode of our Mathematics for SS3 course, we are going to be dealing with the length, the area, and the volume of both plane and solid shapes. Now, plane and solid shapes. Plane shapes are shapes that are two-dimensional in nature. And two-dimensional shapes are basically those shapes that can be represented simply on a plane surface. So, for example, if I draw a shape on this plane surface, it's going to be a two-dimensional shape, right? And they only have their length and their breadth. But then, when we talk about solid shapes have three dimensions. In other words, they are three-dimensional shapes. And those solid shapes, they are like real life figure. They are real in nature. They are real when you look at them. And these solid shapes, they have both length, they have breadth, and they have height. Now, this height is also known as the depth. The depth or the height of a shape is basically what makes us know that it is three-dimensional. So, three-dimensional is separated and distinguished from two-dimensional by the presence and the existence of the height or depth of a surface or of an object. Now let's talk about the we'll talk about the formulas, and these formulas have to do with the perimeter and area of plane shapes. Now if we're talking about plane shapes can be defined only by their perimeters and their areas. Plane shapes do not have volume because they are not three-dimensional. So always remember that plane shapes do not have volume. They are two-dimensional shapes. Now when we talk about these plane shapes, they include your square, your rectangle, your triangle, your trapezium, your rhombus, your kite, and so on and so forth. Now, and also you have your circle, is also a plane shape. Now let's talk about your square. Now this table is a table of the perimeter and the area of plane shapes. For your square has a perimeter of 4s, where s is the side of the square. Now a square looks like this. A square looks something like this. This is how a square looks, and all sides are equal. So here, when this is s, this will also be s, and when the up is s, the side will also be s. So a square has all sides equal. Then let's go to rectangle. A rectangle has a perimeter of 2 open bracket l plus b, as you can see on the table. That's the dimensions of a rectangle. Then we also have a triangle. A triangle has a perimeter of a plus b plus c. So where the sides are a, b, and c. So if this side is a, this side is b, and this side is c, the perimeter of a triangle will be a plus b plus c. That is the sum of the sides. Next, let's talk about the parallelogram. The perimeter of a parallelogram is also the sum of the sides, or you can also call it 2 open brackets l plus b, where l is the length and b is the breadth. So those are the dimensions. Perimeter, in other words, perimeter is very simple to determine in that it simply involves the addition of all the dimensions, all the sides and dimensions of such a shape. You can see that on this table you can also see your trapezium. A trapezium, though it's not included here, but a trapezium has a perimeter of the sum of all the sides. When you add all the sides, that's the formula. So some of them that they don't have the formula here, you just sum the side, like your triangle. As I said earlier, I mentioned a plus b plus c. That's the summation of all the sides given. Then you have your circle. Your perimeter of a circle is also known as the circumference of a circle, and it's given by 2 pi r. You also have the sector of a circle, which is the perimeter of a sector is 2r plus theta over 360 times 2 pi r. Now the reason for this is that a sector of a circle is when you have a circle and you have a portion of the circle cut out, just like from pizza. When you cut out a sector of pizza from it, then you have this part that you cut out. Now this part that's cut out makes a sector. So if we cut this part out and we cut this part out and we have this one left. So let's cut this part out. Let's cut this out. When we cut this out, we have what is known as a sector, and this angle subtended by the sector is given as theta. Now, if we were to look for the perimeter, we have to add every dimension. So we have to add the length of this curved side, which is equals to theta over 360 times 2 pi r. And 2 pi r is the circumference of the whole circle. Then you have to add it to these two lengths. And each of this is r, and this is r too. So this is plus 2r. So that is why the perimeter of a sector is theta over 360 times 2 pi r plus 2r. So that's why it's on that table. Then let's go to area of plane shapes. We have the area of plane shapes as the area of a square is s squared, the area of a rectangle is length times breadth, the area of a triangle is half base times height. Now for the triangle, there are different forms of area. You can also express it as 1 over 2 AB cos AB sine theta, where A and B are adjacent sides and theta is the included angle between those sides. For example, if I have this A and B and I have an angle theta here, theta must be between A and B. So the area will be 1 half A times B times sine theta, the included angle. So there are other ways you can look for the area of a triangle. For example, using Hurray's formula, but we won't be going there in this video because it is not necessary. Then let's talk about the parallelogram. It has an area of base times height. Then we also have the trapezium, has an area of half open bracket A plus B close bracket H. So A and B are used to represent the parallel sides of a trapezium, because a trapezium is made up of parallel sides, one pair of parallel sides. So those parallel sides, their length are known as A and B. And then we also have the circle. The area of the circle is pi r squared. Very simple. This is something you would have been taught many times if you've attended secondary school or junior secondary school. Then let's talk about the sector. The area of the sector is theta over 360 times pi r squared. You can see that your sector is basically just taken as both the perimeter and the area of the sector are taken from the proportions of your circle. Now that is all for your plane shapes. Let's talk about your solid shapes. Now the solid shapes, they are shapes that have both length, they have breadth, and they have height. For example, let's talk about the sphere. Now the sphere is basically the three-dimensional shape of a circle. When you take a circle to 3 dimensions, you get a sphere. Or rather, let me reverse it. When you take the 2-dimensional shape of a sphere, you get a circle. And then we also have the cuboid. The cuboid is also known as the 3-dimensional shape of a rectangle. So the cuboid, every face of a cuboid is in the shape of a rectangle. Then a sphere is simply any projection in any plane. If you project the shape of a sphere in any plane, you get a circle. That is why whenever we have an eclipse of the earth or of the moon, you will notice that the shape formed on the earth or on the moon is circular, because the earth and the moon, they are like spheres. So these spheres, they cast their shadows, and that is geography, but not today. That is geography, but that is simply an area where you can see that mathematics has also been applied. Now these solid shapes include your sphere, your cuboid, your cube, your prism, your cylinder, cone, sphere, and so on and so forth. Now for your cube, you can see on that table, you can see the volume of and surface area of this shape. Your cube has a surface area of 6s squared. Now your surface area can be derived from your ordinary dimensions of the cube. You can build up the surface area, because surface area is simply the addition of the area of every face of that cube. Then your volume of a cube is s cubed. So that is simple to understand. It's simply the product of the length, the breadth, and the height. But in this case, because the length is equal to the breadth and because the length is equal to the height, so that means everything is s. That means we have s times s times s. That would be s cubed. So this is the simple derivation of some of these areas. Then we have a cuboid. The cuboid, surface area of a cuboid is 2 open brackets LB plus BH plus LH. So your L is your length, your B is your breadth, and your H is your height. Now let's talk about your volume. Your volume of a cuboid is length times breadth times height, then so on and so forth. So these are the table. You can see that down the table we also have the surface area and volume of each other shape of that constitute a solid shape in mathematics. Now, having gone this far, let's talk about the fact that this solid shape, we are not stopping here in this video. We are going to take this further, because these solid shapes, they can be formed, they can be joined together to form composite solids, and the volume of these composite solids can be gotten from the addition of the volume of the constitutional shapes. That is the shapes that were joined together. For example, if you join a cone with a rectangle to form a shape, the volume of that resulting shape will be the sum of the volume of the cone and the volume of the rectangle. So that's simply how it works. But then if we're talking about the surface area, you just need to add the area of every face of that composite shape. So we'll talk about that in an example in this video, but let's move on. The volume of hollow shapes are found by using subtraction method. For example, if you've ever heard of a frustum is gotten whenever you subtract the volume of a smaller cone from the volume of a bigger cone. So when you remove a smaller cone from a bigger cone, you get a frustum. And a frustum, you always get the volume of a frustum by subtracting the respective volumes of those initial cones. So then we have the shape of a solid or liquid may change without changing volume. So now this knowledge that if you are talking about manufacturing of many of these plastics and all these shapes, now the volume of the plastic and pellets, the pellets that were fed into the machine, that were melted to form your various plastic items and utensils, just like your plastic bowls, your plastic cups, your plastic spoons, all those shapes, they were formed by all these pellets, and the volume of these pellets, they were transformed without change, assuming that there was no diminishing. Assuming there was no diminishing of the volume, assuming there was no reduction, assuming there was no volume of the material loss. When you convert a shape from a solid shape from one form to another, you are not changing the volume. So, for example, we are going to use this knowledge to solve a lot of questions in this episode, and then you have to stay put. You have to keep with me until the end of this video so that you can gain as much as possible. Then, lastly, let's talk about the application of all these addition and subtraction of shapes volumes. So now let's demonstrate each of the concepts I've talked about in this video. Let's demonstrate it in 3 examples. Now the first example, example 1, which I'll be giving, is figure 4.2 shows a doorway made up of a circular arc AB, which subtends an angle of 60 degrees at center O, 2 uprights CD and AE of length 4 meter and a horizontal base ED 3 meter wide. You can see the shape. The shape is in the shape of a rectangle in conjunction with a circle. So a circular arc is a circular arc. So when you put the circular arc on top of the rectangle, you get a new shape, and this is called a composite shape. Now this composite shape, it has dimensions. For example, you have the DC is 4 meter, your AE is 4 meter, your DE is what's called is 3 meter. Then your CA or your AC is like an arc, so we'll just leave it there. So then we are asked to show that the perimeter of the doorway is 11 plus pi meters, and then the second question says we are asked to find a similar expression for the area of the doorway in meter square. Now that first part we are looking for the perimeter, and the second part we are looking for an expression for the area. Now the solution goes thus. You can see that in this triangle, in this shape, you can see that in triangle OAC. Just follow me in this solution. Let's solve it analytically. So you can see that in triangle OAC, AC is equal to 3 meter. You can see that AC is 3 meter. Now because they are parallel sides. So and then because they are opposite sides of a rectangle, because this shape is a rectangle, the bottom of the shape. Now then we also have that OA is also 3 meter, because OCA is an equilateral triangle. So you can see that because that is 60 degrees, and because those angles will be equal, so OCA is an equilateral triangle. So OA will be 3 meter, and AC is 3. So AC is 3, OA is also 3. So that's true. And then we also have arc ABC is what? The length of arc ABC will be 60 over 360 times 2 pi times 3 meter. So that would be the length of arc ABC, because the length of an arc is theta over 360 times 2 pi times the radius of the circle. So when we evaluate that, we have the perimeter of the doorway will be equals to CD plus DE plus AE plus arc ABC, and we know that when we add everything together, arc ABC is what? Is pi. So that will be 4 plus 3 plus 4 plus pi. That's 11 plus pi. So we have successfully shown that the perimeter of this shape is 11 plus pi meters. Then let's move on to the next question. The next question says we are looking for a similar expression for the area. So what we need to do is we are going to, you know that in composite figures, I mentioned earlier that you are going to add the areas together. So you are going to add the area of the circular sector plus the area of the rectangle. So now the area of the sector is given by theta over 360 times by r square, right? So here we have 60, theta is 60 degrees at the center, 60 over 360 times pi, r is 3, so that's pi times 3 square. So when we evaluate that, you have 3 over 2 pi meter square. Then next, the area of the segment is equal to area of the OABC minus triangle OAC. So when you're looking for the area of this segment here, you have to subtract the area of the triangle from the area of the entire sector. So that's when you get the area of the segment ABC. Now when you subtract it, you can see you get your answer as 3 over 2 pi minus 9 root 3 over 4 meter square. So that is the expression for the segment. And then the area of the door will be equal to the area of the rectangle plus the area of the segment. That will be 3 times 4, because area of the rectangle is length times breadth, right? That's why it's 3 times 4, then plus area of the segment, which we've gotten earlier to be 3 over 2 pi minus 9 root 3 over 4. So when you add everything, you get the expression for the area of that shape. Now I hope you understood that illustration and that example. Now that example is under composite shape. Let's go on to another example on this in this video. And then this second example, we are going to be talking about when we we are going to be applying the knowledge of volume to look for the mass of substance given their density. Now if you don't know this, there's a relationship between mass, volume and density. The relationship is thus: the density of a substance is equals to the mass divided by the volume. So in this case, when we are looking for the mass will be what? The density, the product of the density and the volume. Now the question goes thus: a brass rivet is composed of a cylindrical shaft and a hemispherical cap with the dimensions as given. So we have this the rivet, and it's composed of a cylindrical shaft. So this is the shaft of the rivet. The shaft is different from the head. So this shaft, we have the shaft and then we have the head. Now the shaft is cylindrical and the head is hemispherical. So what you need to do is you are just going to add the volume of each of these, and then when you get the volume, you are going to multiply by the density to get the mass. So let's solve the question. So here we have the volume of the rivet is equal to the volume of the hemisphere plus the volume of the cylinder, right? So that will be volume of the hemisphere is half the volume of a sphere, right? Hemisphere means when you cut a sphere into two. So the hemisphere will be half of the volume, and that is 2 over 3 pi r cube. So that's it here, you can see it. Then you now add that to the volume of the cylinder, which is given by pi r square h. So you can see that pi is there, then r, the radius of the cylinder, will be equals to 1 over 4 because the diameter is 1 over 2. Then pi r times square times the height. The height is 1.5. That's when we evaluate everything, we will get this expression: 17 pi over 4 times 24. That's 17 pi over 4 times 24 centimeter. And then the mass of one rivet will be equal to 17 pi over 4 times 24, then multiplied by 2.4 grams. So the reason why I'm multiplying by 2.4 grams is because in order to get the mass, you have to multiply the density and the volume. So the mass will be equal to the product of the density times the volume. And the density is 8.4 and the volume is 17 pi over 4 times 24. That will be 17 pi over 96. So when we evaluate all that, we will get our answers. When we substitute 20 over 7 for pi, our total answer is 4.7 kilograms to two significant figures. So you can see that this example shows how you can manipulate the not just the volume but also the density and the mass to calculate the mass of a substance. Then finally, let's talk about another application where we're talking about what if we change the shape of a solid. Now in certain circumstances, the shape of a solid or a liquid may change while its volume remains unchanged. For example, a metal block may be melted and recast into a different shape. A liquid may be poured from one container to another, or the level of the liquid in a container may change if something is immersed in the liquid. Now let me give this example. In this case, a silver disc 5 mm thick and 8 cm in diameter is melted and pulled out into a wire. So now you are converting a disc from a disc into a wire. So you can see that a disc is actually a flat circular surface. Then you are turning it into a wire, and a wire is like a cylinder with a very tiny radius. So that's a wire. The wire is just a cylinder with a small radius. So and then we have to look for the length of the wire. Now in this case, you are converting from a disc to a wire. So now the volume of the wire will be equal to the volume of the disc, because there's no loss of volume. When you change shape, you don't lose volume. So that means the volume of the wire is pi r square h. So because the wire is a cylinder, the volume of the cylinder is pi r square h. So volume of the wire is equal to volume of the wire, Vw, equals the volume of the volume of the disc, Vd. So but volume of the wire is equals to volume of a cylinder, that's pi r square h, equals to volume of the disc. The disc is in form of a circle, so that will be the volume of that circle. When you calculate it, it will be just like a sphere. So the volume of that disc, it will be the area of the base times the height. The volume of the disc is also like a cylinder too. That will be pi r square h. Pi r square h. So you can see in this example, we have the radius of the wire as is given as 0.05 when we converted it to meter, 0.05 meter. Then we also have the radius of the disc is 4, and then the height of the disc is, or the height is also known as the thickness. The thickness of the disc is 5 millimeter. When you convert it, that would be 0.5. So whenever you do that, when you do that, you will get so this, our answer in centimeter is 3,200, and when we divide by 100, we will get our answer in meters, which is 32 meters. So this is another application of the volume and change of volume of shapes. So from what I'm trying to say in this video is that, what I've been trying to say so far, the summary of everything I've been trying to say is that anytime you have your plane shapes and your solid shapes, anytime you sum your volumes, anytime you add two plane shapes together, you will get a composite shape. And though that composite shape, you can always get it by adding the volume of the corresponding shapes. And then in same vein, anytime you melt or you change the shape of a solid, you are not changing the volume. So in that case, you are going to set up an equation such that the volume of the first shape will be equal to the volume of the second shape, vs1 equals vs2. So that is simply what we're trying to say here. Now, I hope you've been able to understand and you'll be able to gain something from this video, even though it might look as if it's a little bit advanced or ununderstandable, but it is still something that you should be able to grasp. And hopefully, if you have more, if you want to get more information and you want to learn more about this topic, you can also try to reach me out by checking out my number on the channel. So thank you for watching, and see you next episode.